Hello, everyone. Welcome to the talk on leveraging deep learning and video analysis in law enforcement. I'm Sanchit Arora. I'm the lead researcher in the Axon Research group. A little bit of background about myself. I was a co-founder and CTO at Dextro. At Dextro, we were building video analysis solutions using the latest advances in deep learning, but mainly catering to the media publication space. We were acquired by Axon earlier this year to bring the technology that we had built as part of Dextro towards law enforcement, mainly helping all of the video that gets recorded via body-worn cameras that officers across the country are wearing and help improve their workflow. So today I'm going to talk a little bit about the kind of products that Axon builds, how machine learning is an integral part of all of those products, and how we are improving the workflows for officers across the country, making their lives easier so that they can focus on the work that they're supposed to be doing. I'm going to share my screen now. Great. So, as I said, my talk is on leveraging deep learning and video analysis in law enforcement. I'm Sanchit Arora. That's my email. In case there are any questions or anything that anyone needs to talk to me about, they can reach out to me on that email. Quickly going over the agenda to know what I'll be talking about here. First, I'll give you a brief overview of what Axon builds, all the products and services that we provide. Then move on to all of the law enforcement challenges that we see on a daily basis by interacting with police officers and all of the agencies. Then I'll focus more on the machine learning solutions that we've built for some of the challenges that we found to be most impactful. I'll walk through the process and approach that we took to come up with those solutions. So deep diving into the models that we use, the kind of data collection pipelines that we've set up, the ontology that is very, very specific to law enforcement, and other things. Once I go through the process, I'd also want to highlight some of the unique challenges that are only relevant for law enforcement. I feel they're very, very important because a lot of the other domains do not face the same kind of problems. So solutions that we build just specific to these needs are also very, very relevant. I'd like to end the talk with how we are moving forward, other kinds of solutions that we are looking to build in the future. Starting with a general background of Axon. Axon is much more than just building devices. It's an ecosystem where devices, services, and people are thought of as being interconnected through an entire network. Our aim is to revolutionize public safety around the world. Axon was previously known as Taser. We used to build conducted electrical weapons. Our aim was to get rid of the bullet. But as law enforcement and public safety has grown in scope, we've increased the kind of services and products that we offer. And our latest offering is a body-worn camera. We believe the body-worn cameras that we build are the most rugged and most useful to law enforcement agencies. These cameras are specially designed for law enforcement officers to wear throughout the day, throughout the shift that they're on. They are designed to get out of the way. They turn on by a simple double tap. They record video. They also buffer video, wherein we need to get context for a particular event that happened that an officer just reached on. And all of that video is synced via a bunch of our services that I'll be talking about. Other products that Axon builds are a Flex 2 camera. This camera is a point of view camera. It can be worn on sunglasses, on a cap, on the collar, or shoulders. And this allows officers to record point of view video, which is in some cases much more informative than body-worn video, where the body-worn camera is worn on the chest. We also built a signal sensor, which we call the signal sidearm. This sensor interacts with the holster. Departments that have still not moved on to the Taser gun and are using, say, other weapons, how do we interface with those weapons such that whenever those weapons are drawn, we get a signal and we are able to turn on our cameras. This is the kind of signal sensor that enables that. Another product that is very new and we're building for law enforcement agencies is the Axon Fleet. This is an in-car solution. Police cars can be fitted with body-worn cameras or now specially designed cameras for these cars, such that any incident that the officer arrives on in his car is also captured by cameras within the car. We are also building cameras such that they can look at any suspects or any action that happens on the back seat of the car. The aim is for the car to be equally supportive to the officer as he performs his duties on the field. Supporting all of these hardware devices is our cloud services. The biggest cloud service that we have is evidence.com. This is a single shop for all evidence data that an officer collects about any event that happens in the field. So, for example, any event that the officer recorded on their body on camera, once their shift is over and they get back to their department, they can dock the camera. All of the video from the camera is uploaded to the cloud seamlessly without the officer having to interact with the camera. They're associated with the particular officer. They have information about where the video was taken, what time of day it was. If we have information about an event ID, the video is automatically linked to the event ID. At the end of the day, the officer is able to go in, log on to his account, be able to see all the videos for any particular events that he was part of. Makes it very, very easy to share video as well. So if an officer wants to share a video with any of his supervisors, any other departments that are relevant, they can easily do that. Along with the cloud services, we provide a mobile app. The mobile app allows the officer to stay connected with their Axon cameras. They also allow them to look at what the camera is seeing in case they want to test it out or make sure that they are able to capture the unique aspects of a particular scene. And the camera also allows them to review any video evidence that they recorded. So after the fact of a particular incident, they can go in, check out the video, make sure that the video gets tagged properly, is associated with the right kind of account. So that's an overview of all of the services and products that Axon builds. I want to jump into some of the unique law enforcement related challenges now. We realize that we have the opportunity to bring a new level of rigor and automation to law enforcement. With the adoption of the body-worn cameras that we build, we've seen like an exponential year-on-year growth in body-worn video. A lot of our customers, although very excited about the kind of information that they get through these body-worn cameras, feel that they're not taking full advantage of their data. At times, big departments are overwhelmed with the amount of information they have. Imagine a department with more than 1,000 officers on duty at a particular time, each of which on an 8-hour shift. Even if they record video for about 2 hours, that's more than 2,500 hours of video per day, per shift. So that's a lot of video for anyone to manually be able to look at or take advantage of. Other effects of such huge amounts of video has been that there's been very, very high costs associated with supporting FOIA. FOIA or the Freedom of Information Act allows citizens or anyone to essentially ask for evidence associated with any particular case to be released into public domain. The main consequence of wanting to release that information is that any private information that has been captured by these cameras needs to be redacted. Redaction, in the most basic sense, means either you need to make sure that there is no private information associated with the evidence being released, or it is being blurred to the point where no one else can access that content. So currently, officers employ a huge amount of secondary workforce that goes through the video and is able to redact all of the private content. Private content in this scenario means faces, driving licenses, MDTs, which are the mobile devices that they have in their cars, any license plates, all of that information. The bigger cost here is that building a single solution does not help. Different states have different criteria for what kind of things they need to redact, and a customized solution for each one also is very, very hard. What this has led to is, given that technology and no automated solutions exist, police departments are hiring more and more officers to do these kind of manual tasks. These officers are spending more than 70 to 80% of their time just going through data that has been recorded on field, trying to serve FOIA requests, trying to make sure protocols are followed, trying to make sure that data which does not help anyone else is being removed or being moved on to prosecutors in a timely manner. The manual data tasks, as I talked before, include redaction. This has turned out to be one of the most urgent needs for our customers. Blurring faces, license plates is the first step. Identifying any subtler forms of information where someone's name is being called out, or you are talking about a license plate number, all of those information is still part of the video, and there is no real way for someone to automatically go in and get rid of that information. The other manual task that is very, very prevalent in the field is search. Reasons to search through the video are many. People want to do FOIA, people want to investigate a particular case, they want to look for a particular incident that happened. Reports that the officers write on the field are also very, very limited. They need to go through all of the scenarios. It's heavy on paperwork. They are distracted while the incident may be changing. Moving on to the kind of machine learning solutions that we're trying to build to solve some of these problems. The first one that we want to target towards redaction has been assisted and automated redaction. Although we have an automated solution at this point, which can detect faces, license plates, NBTs, that's not a complete solution, mainly because there is a lot of regulations that require police departments to actually manually review any redaction that happens. That's why we've also built an assistive solution. An assistive solution takes advantage of things like tracking. And given an initial manual input on an object that an officer wants to redact, we can track the object through the video using tracking algorithms that make the task much easier. At this point, I want to give a brief demo of the solution that we've built. So what we see here is instead of us in an automated way removing all of the information that we want, the user is manually able to tag parts of the video that they want to redact. For example, here the officer tagged the face and a mailbox. Both of these are identifying information. We are able to track those without knowing that this is a face or this is a mailbox. Just by initial input from the officer, we're able to pull back any of the private information that is being recorded as part of the video. The next portion of the machine learning solutions that we're building are automated tagging for videos. This is not limited to just saying that this video is about a particular incident, although that is a very, very important use case. We are going even deeper, where within a video, we can identify which part of the video is related to what event. For example, say there is a traffic stop. We are able to identify which part of the video the officer is driving to the traffic stop, where is he actually interacting with the offender, where in the video is the officer putting down the ticket, where did he ask for the license. All of these time stops are clearly identified and marked. This makes the job of the supervisor very, very easy. In case they want to go in and make sure that the officer followed protocol, they're able to jump right to the point where a particular incident happened. We can also tag things like use of force or use of any weapons. This allows officers to very, very quickly go through all of their videos instead of having to watch all of them. We can flag them directly for the officer to take any action that is needed. The third kind of thing that we are building is a summarization highlights tool. This is a work in progress, although we see a lot of demand for something like this in the field. A good segue towards why the solution is important is the fact that most incidents that happen in the field are anywhere between 10 to 15 minutes long. 10 to 15 minutes of an officer's time at the field is probably important, but someone reviewing the video already knows a lot of the video is not useful. For example, a lot of the video is the officer just driving to the incident. So we wanted to come up with a way where we only focus on the main areas of the video that are most relevant for someone who's watching the video post the incident to look at. Summarization and highlights is an extension of this thinking, wherein using highlights, we are able to identify places in the video which should be watched by a supervisor, for example, use of force or drawing of any weapons. And summarization gives a quick overview of what happened throughout the video. So anyone, before they jump into watching the whole video, gets a brief context of what the video is about and what they can expect. As I talked about, Redaction is one of the main tools that we're building. I shared our demo from there. The other tool that we are building along with Redaction is the license plate recognition. This allows officers to be able to track any license plates that are in the field. This is a solution that we're building along with the fleet, which is the in-car solution that we have. If cameras on the car can track any license plates that are either being tracked or being looked for when moving around during the city, during the day, that's important and a good use case for police officers to solve. Jumping into our process and approach, some of these solutions have lots of intricacies. The one that I'm going to focus on today is the tagging of the videos, since that's been our major push for this year. Starting out with the ontology. The ontology is a very, very important component of any machine learning pipeline. Anyone who's built a classification system in the past understands the importance of an ontology. For example, if I look at academic datasets like ImageNet or YouTube, they have a list of tags that are associated with the content that you're looking for. For us to understand law enforcement data, the most important aspect was understanding what in the law enforcement data matters to us. Some examples from our ontology are incidents. Incidents are reports that officers file about particular things that happen. For example, a traffic stop is an incident. So this is an event involving one or more law enforcement officers in a patrol vehicle, temporarily stopping another vehicle, walking up to ask them about anything that they find wrong with the situation. For example, tail light is broken, or the driver was speeding, or anything like that. A pursuit is an event involving one or more officers in a patrol vehicle attempting to apprehend a suspect. So a lot of high-speed chases are part of these, or someone who maybe they tried to stop for a traffic stop but ran away, and so on. A pedestrian stop is an event involving one or more law enforcement officers on foot, on a bicycle, or in patrol vehicles where instead of stopping a car, they're stopping pedestrians in the field. This could be for any violations that the pedestrian is suspected of, or if the officer is trying to gather any information. Note that these are some examples of the ontology we are building. Across the country, we have a lot of differences between what a traffic stop constitutes, and capturing that was also a big part of building out our ontology. So, for example, a traffic stop could start with the officer driving in a car, but there is a lot of other steps that happen post that. We end up with officer walking to a stopped car, the officer talking to the driver of the stopped car, the officer walking back to the police car, the officer typing stopped vehicle information on his computer, the officer walking to the stopped car again, the officer handing ticket to the stopped car driver, and so on. Note that not all traffic stops follow this process. We might see some variations, but this is roughly the kind of things that we hope to be seeing within a particular traffic stop video. So the team that we built out for ontology building works on building out scenarios for each of these incidents. So say there's a traffic stop, there's a pursuit, there is a pedestrian stop. What are the kind of things that we can see? We also try to map it out into a tree structure, which gives us a sense of things, how we want to see them in order. The next thing after having an ontology or having known the kind of things that you want to detect in a video is being able to collect data for that particular ontology. Data collection is an important part of any machine learning pipeline. Given the security and clearance requirements for being able to view these videos, we are setting up a small in-house team to annotate our videos with the categories and segments that are part of our ontology. Given the security and clearance, it's very, very hard for us to use any of the crowdsourcing platforms that allow big data sets like ImageNet or YouTube 8 million to be set up. Our data annotation work involves setting up this team. We are also building out annotation tools. Essentially, given a video, as you see on the right-hand side, on the left-hand side, the user of the interface is able to mark out all of the different segments of the video with information that they see. After having extracted and collected all of this data, our next step is to be able to build a feature pipeline. The feature pipeline allows us to extract all of the features that we think are most relevant for a video for us to classify it into the different ontology segments that we previously highlighted. There are three different areas that we look for in terms of feature development. A video, we look at a video as consisting of three different parts. There's the visual components, there's the motion components, and there's the audio. I'm including speech as well as non-speech clues and bundling them together as audio. For us, the non-speech also plays a big part in identifying video content. For example, a siren in the background, or a honk, or a revving of the car, or things like a gunshot, or someone shouting out any commands are important things for us to be able to identify. A deep learning pipeline extracts visual features by using like a standard conv net. The example that I have here is the inception net. This allows us, if we remove the classification portions of it, which are essentially the last couple of layers, we're able to use the network as a feature extractor. We have tried using pre-trained networks, and we've also trained our own networks on the data that we've collected. Given the kind of information that we can extract from our own data, we've found feature extractors based on our data to be much more useful. Although for simpler experiments, the research team has also focused on extracting features which are based on any of the pre-trained networks. We get like a noticeable boost in performance by using features extracted from our own networks. And that's why the production pipelines usually carry those. But to be able to prove out, say, a particular model doing well, we are able to use existing networks as easily as possible. To capture any information that the motion of a particular motion features in a particular video capture, we focus on two different known motion features. The first one is optical flow, and the second one is C3D. C3D is basically a 3D convolution. It's based on the idea that instead of using a single image, you can use a set of images to extract how the images are varying. And if you pass this a set of consecutive frames from a video, you can extract motion information. In practice, however, C3D ends up being much more computationally expensive. Optical flow gives us a lot more advantage because we can sample based on how much complexity we are willing to live with. Also, another point to note here would be that if we look at the latest advances in action recognition and video understanding, some of the top performing networks use optical flows in a two-stream performing networks. The third feature, which was the audio, we use both the speech and the non-speech components. The speech components or the speech features that we extract are based on transcripts. Two different transcript services that we've used in the past include SpeakWrite and Carly. SpeakWrite is like a CGIS compliant transcript service. It's human annotations. So we have the company provides human annotated transcripts where people are sitting and listening to the audio and annotating them. Carly is a pure software-based solution. Performance-wise, it is highly performant. The turnaround time is very, very quick. However, the quality is not as great as a human annotation would provide. And thus, in our pipeline, we are able to compare what a human and a machine solution are able to give. For non-speech features, we prefer to go with SoundNet or MFCC. The MFCC gives us a frequency distribution over different ranges. SoundNet was a network that was recently trained and is able to identify sounds from a varied set of features. I'm going to jump into. Sorry, I was told that the slides were not changing. Was that the case? I'm quickly going to jump into the kind of information that we can extract from sounds. So people who are unaware of SoundNet, so these are the kind of features that we see from there. For example, what do dog-like sounds sound? What are music-like sounds? What are car-like sounds? So this network is able to differentiate between all of these different sounds. And using that as a feature has helped our machine learning pipeline understand the video much better. Quickly going over the models that are part of our pipeline. For law enforcement, we mainly use 4 different classification models. A dense audio video, a dense split audio video, one directional LSTM, and a 2-layer LSTM. And for segment classification, we've used LSTMs with combination of an inner attention layer and something that we call an R-class LSTM. So a dense audio video model takes an input as a normalized audio and visual features and builds a 2-layer densely connected network. A dense split audio video network does not try to combine the audio and video and learns them as separate inputs, and only at the pre-final full layer the connectivity for both audio and video happens. Then we use LSTMs based on bag of words, and we also use bidirectional LSTMs. The bidirectional LSTMs are useful because we have pre-recorded videos. They may not be as useful if we move on to the live streaming phase. But in pre-recorded, we can gain much more information about the current state from the past and the future states, which the bidirectional LSTMs provide. For segment-based models, we focused on something that we call an inner retention layer. Most of the current work on inner retention happens in the spatial domain. This is where, given a particular video, or an image, you can find a particular spatial spot in the image to focus on. If you look at the example on the right-hand side, since the boy is juggling the football, the focus of the network becomes the football. So this is something that we call spatial attention. For our use case, we focus on temporal attention. So what we are saying that there are certain parts of the video in the temporal domain that we want to use to classify what the current segment is about. The second segment model that we use is the R-class based LSTM model. This takes the input as an audio and video feature as well. The hourglass shape of the model allows us to distill information in the current input into most relevant and then try to classify the current segment. This is also inspired by some of the work that people did on the spatial domain. An important work is by Terry from who's a PhD student at University of Waterloo, and his work on semantic segmentation used some of the work that we also try to incorporate into the temporal domain. After we build all of these models, it's very important for us to present the output in a way that is easy to consume by law enforcement agencies. Hence, timeline smoothing is a very important part of our pipeline. If we know that a particular incident is a consequence of things that happened in the past, we can associate the fact that unless the officer gets out of the car, he cannot be walking over to the suspect car. So this allows us to smoothen our final output by applying a smoothing constraint on top of any timeline results that we get. As people who are aware of most machine learning pipelines, evaluation of a particular model is very, very important. We evaluate our models quantitatively, which gives us numerical information about how well our models are doing. For example, for a sample set of videos that we ran our experiments over with just the three categories, we come up with information on how easy it is to confuse between the three categories. Other information that we extract is given a particular ensemble of say five different networks, is how often is everything in the ensemble wrong. This is highlighted in the top right graph in the particular slide, where we are saying that roughly 20% or roughly 20 images from 20 videos from our data set were wrongly classified by all five of the models in the ensemble. This gives us a sense of the fact that there are videos that are not being captured by any of the models in our ensemble, and gives us more direction in terms of improvements that we want to make. Given limited time, I'm going to quickly run over the unique challenges. As we talked about the ontology, we needed to be very, very specific to law enforcement. Data access and annotation, we do not have any existing data sets for law enforcement, and we cannot use any crowdsourcing due to the security and compliance requirements, which allows us to go through all of these different steps on our own by setting up our internal workflows. Egocentric video, which is video that is recorded by our body-worn cameras, there's very limited work in academia and the community. The videos are shaky, blurry. There are fisheye distortions, given that the camera tries to capture a large field of view. And all of these are challenges that we need to deal with on a daily basis. The current regulations also require us to move towards assisted automation rather than complete automation. This is because any automation that we do eventually needs to be manually tested and inspected. Hence, our aim has been to automate with trust. How can we build trust with the users of these technologies such that they are able to trust us with their output? Moving forward, what do we see other areas where machine learning can help law enforcement do better? Things that are in the works is an automatic license plate reading solution. This is an end-to-end solution that we're building with Fleet that would capture all of the information related to license plates within the car itself without needing an external solution. We're also trying to build real-time camera response systems. Our current cameras are not able to do much machine learning on the device itself, but as our cameras become better and are able to do more processing online, can we take actions based on real-time detections? For example, if we hear a gunshot in the background, can we turn on the camera automatically? Other cases that can be supported then are based on live streaming, which is also something that we want to consider our cameras to be able to do in the future. The final golden holy grail of being able to understand videos is move on to automated report writing. This would reduce the officer paperwork by a huge amount and uh, give us the most complete picture of what is happening in the video. A quick thing that I want to touch upon is the fact that our work is not limited to just our products. It's also a responsibility to ensure we're not releasing products that put our customers in compromising positions. We want to work with our officers and our communities to make sure we are benefiting both. An example of this is facial recognition. The ethics behind facial recognition in law enforcement is very tricky. We definitely see the value, but we want to explore these technologies smartly and ethically. That's why we are instituting an ethics board so we can get these technologies right for law enforcement and the communities they serve. This would be a completely independent review team. They would come from varying backgrounds and perspectives. So, people from the community, people who've served in law enforcement in the past, people who've been working in um, machine learning for a while, and they would provide the guiding principles for development of our work. Thanks. That would be the end of the talk. I want to see a couple of questions that came up. So one of the questions that someone asked was, what are some examples of vendors doing ML to flag events in video? So our current vendors include police departments. A lot of police departments are doing machine learning to flag events in video. Some of the big departments that we work with include LAPD, Seattle PD, Arizona, New York. So all of these are doing things to flag events, not necessarily in an automated way as yet, but they're looking to grow how much automation they can bring into their current workflows. Another question that Tim asked was, could the video scan live footage and send alerts to police stations or the public? That's a very good question. I just highlighted that as part of things that we want to do moving forward. Our current solutions that we provide, our cameras are not able to scan the footage live, but that's something that we aspire to do. Moving forward, we are trying to build that capability within our cameras such that they can scan any live footage and send alerts to police stations or the public, or even during an incident, they're able to inform the officer in case they were not paying attention. Another question that just came up is, can we highlight the underlying technology infrastructure? Yep, totally. So we currently, our infrastructure is built on top of TensorFlow. I did not highlight that mainly because a lot of frameworks already exist, and it is not that we think that one framework is better than the other. Just that there is a lot of flow support for TensorFlow out there, a lot of great community work that's happening there. It was a framework that we picked up and have continued to build our solutions on top of. We also support other frameworks within the research group. For example, we have researchers who work with MXNet, people who work with Torch, but our production infrastructure all uses TensorFlow. I hope you guys enjoyed the talk. Thank you so much for joining in. And in case you have any questions, feel free to reach out to me on my email. Yep, you can reach out to me on sarora@axon.com in case you have any questions or need to know anything more about how we are building machine learning and deep learning based solutions for law enforcement. Thank you and have a good day.